All right, we're finishing up section 2.8 here. It's only got two main parts. One of them we looked at yesterday, where we're adding, subtracting, multiplying, dividing functions. And then today we're talking about function composition. So let's jump in. Just take a look at this. You don't have to copy it down or anything. Just take a look at it, read it, see if it makes sense. Okay, notice something. Look at the notation here. The way I'd say that is f of g of x. F of g of x. Thinking of it like that, I'm working the parentheses inside out. And so I'm going to send something to g. Just looking at the notation here. I'm going to send an input to g. G is going to produce some output. And then I'm going to send that output to f. And their little drawing down here illustrates it really well. I'm sending something into g. G, being a function, is going to send me one thing back, right? I'm going to take that one thing that it sends out. So think of that g of x right there as a y. I'm going to take g's y and send it into f as f's input. So g's handing off to f. Then f takes that input and produces some output. This would be the y of f here. It's just chaining it along. In other words, the output of g becomes the input of f. Anything like that in the real world? The example I used, period 1, was suppose we have a microphone. What does it do? You're singing into it. You're producing sound waves. This is just like a picture, isn't it? I mean, the skill level of my drawings. You sing into it, you're producing sound waves. The microphone's function, it's a function. The microphone's job is to translate those sound waves to electrical impulses. So it's got a cord coming from it. And the microphone is saying, okay, you're sending me sound waves. I'm sending out, as my output, electrical signals. What happens then? Well, a whole bunch of singers now that sound like they can sing are running through a thing called auto-tune, which takes their crummy singing and changes it to something melodic. So now then, notice what happens. The auto-tune unit takes the microphone's output, changes it into something pretty. Then what? Then it goes to a PA system, which is an amplifier. And then it goes out to speakers. And as crude as that analogy might be, it's not a bad one. The microphone's input is your voice. The microphone's output is electricity. The auto-tune's input is that electricity. It changes it into better electricity. Goes into the PA amp. The PA amp's input is an electrical signal. It does what? It steps it up in volume. Sends its output to the speaker's input is the output from the PA amp. What's the speaker's job? It changes that electrical energy it's getting back into sound waves. quite a process. And most PA systems are a lot more complex than that. But this is exactly what we're talking about when we're looking back here. One function's input is coming from another function. That's all it's saying. So far, so good. We get to here, and it still looks okay. Notice there's two different ways of writing this composite function idea. This one right here is the one I like because it actually says what's going on. This says, give an input to G. G is going to produce an output. Send that output to F as an input. Here's what the book uses a whole lot. It's okay. I don't like it as much because it looks like F comes first. It doesn't. G comes first there in that lineup. Then here's where we hit a sticking point in period 1. Figuring out the domain of this composite function. And it's a set of all numbers. Now, we're going to come back to this. In the domain of G, remember G comes first, so that the output from G is in the domain of F. Honestly, I had to read that about 5 or 6 times before it made sense. It's all the numbers in your first function domain, so that when you run those numbers through that first function, you're producing a y value that the second function, in this case F, can use as an input. Let's look and see what that really means. So we have two functions here. They first want us to find f of g of 2. So they're asking us to evaluate this when our input to g is 2. Get that in your head, when our input to g is 2. All right, so g of 2, so I'm really doing this. I think that's a better way to write it. So I'm really saying when I send 2 to g, then what's f going to give me? Well, when I send 2 to g, what do I get? 2 over 2. Right. So now I'm sending a 1 to F. It's just chaining along. If I send a 2 to G, G sends me back a 1. I send that 1 to F, and F gives me what? Let me do this. There's the one I got from G. Equals that. So here's our answer. Now again, we're just evaluating this function at a certain input. Let's turn it around. Now I'm getting g of f of 5. So they're wanting us to evaluate this composite function when I'm sending 5 in as my first input. Notice now I'm sending it to F first, and then F's output goes to G. So I'm looking at F, every place I see an X in F, right here, I'm going to put a 5. like that. If I send a 3 to G as input, I'm getting that. Now notice these two things are not the same. So the order matters greatly. Notice here, they're wanting us to get the composite function, okay, and then figure out its domain. That's where it gets a little weird. So we're going to do something similar here. Notice G is coming first. So I'm really saying f of G of X. That means every place in F that I see in X, I'm replacing it with what I'm going to get as an output from G. Okay, which is this, isn't it? I mean, that 2x plus 5 represents the output I'm going to get from G if I send it an X. All right, so let's see if we can do this. So I've got equals the square root. What am I going to get from G? 2x plus 5. Now notice I'm writing in red what I'm getting from G. So the red represents the output from G being sent to F, and that's replacing the X that's in F. Stop right there. See if that makes sense. Let's look at the domains of F and G. So the domain of F is what? Any restrictions? I could put any number I want to in there for X. No. So there's restrictions. I can't put any negative numbers. Could I put 0? No. So the domain of F now has to be at least as big as 1, and it could get bigger, like that. Right? Because if I send a 1 into F just by itself, I'm going to get 0 under the radical. That's okay. The domain of G. Any restrictions? No, G could be anything because it's just a straight line. All right, so I've got negative infinity, positive infinity. Let's go back and look at something. This thing. All numbers X in the domain of G. So right now, in the one we're working on, G could be anything. The domain of G is all real numbers. But I've got to pick them so that when I send the output of G to F, I get something valid. In other words, the input coming into F has to be a good input. Okay, let's go back. Well, here's my composite function right here. Actually, if I wanted to write it a little bit neater, it could be square root of 2x plus 4, right, when I combine those numbers. There's my composite function. So we did the first part, but now we got to decide what is its domain. In other words, what can I send from G so that that number I've got in the black circle is valid? See, it can't G just anything. I can't send it a whole lot of negative numbers. I can send it any positive number. How do I decide now? I have to pick something in G that when I send its output to F, the thing I've got in the black circle is valid. How do I do that? Well, think of it like this. What do I want in that black circle? I want something that's 0 or bigger under the radical. So I take this and I say, all right, my 2x plus 4 has to be at least as big as 0. Means 2x has to be at least as big as negative 4. And x has to be at least as big as what? Negative 2. Or did I mess up? That looks like it could work. Stop me if I'm wrong. This is so easy to be wrong on. It'll really drive you crazy. Okay, let's check it. Let's just mentally check this. If I send, this is my input to G. If I send a negative 2 to G, what I've got in the blue circle up there, what do I get as output? I've got 2 times negative 2 plus 5.
I thought that if you had the G first, you put it into the F first.
No, that's a good question. Look what's here. I've got to do this part first. This is where it'll send you to the next room talking to yourself. I've got to send an input into G. G is going to give me an output that then I send into F. So I'm trying to decide, what can I send into G? G's domain is anything. But that's not what counts. What counts is the output coming from G going into F. Can it be anything? And the answer is no. That 2x plus 4 has to be at least as big as 0. So let's go back. If I send a negative 2 to G, I get 2 times negative 2. I'm looking at the blue circle up here. 2 times negative 2, which is negative 4 plus 5, which is 1. I'm going to take that 1 and I'm going to send it into F. Let's put that in the red circle up here. If I send a negative 1 into F, what do I have under the radical? 0, which is fine. I can have the square root of 0. If I send in anything bigger than negative 2 to G, am I still okay in F? For instance, if I send a negative 1 to G, then in the blue circle I'd have 2 times negative 1, which is negative 2, plus 5, which is positive 3. If I send a positive 3 into F, the red circle, I'd have 3 take away 1, that's the square root of 2, that's good. So the domain for the whole thing, and I'll notate it like this, is what?
Negative 2.
Yep. This is not very intuitive. And I suggest when you do it, check that boundary number, that -2, by sending it into G, seeing what output you get from that, send that output to F, see if you're okay. And this is weird because G had no restrictions just on itself. F's the one that had the restrictions. Let's look at B. Now I want G of F of X and its domain. So I'm saying, now what comes first? F of X. And that's what Peyton was thinking about. So it means every place in G that has an X, I'm going to replace with F. So I've got 2 times square root of X minus 1 plus 5. I'm looking at G now. Every place I see an X in G, I'm replacing it with F. There's my composite function. Now all we have to do is decide the domain. So let's go up. What's the domain of F? It hadn't changed any, has it? The domains are exactly what they were up here. But now we've got to figure out what's the domain of our composite function. And the question becomes, what'll make that thing in the black circle okay? What values of X? And so what I can do is say, all right, I'm going to do something similar to what we did up there above. I'm going to say, here I've got X minus 1 under the radical, so I know X minus 1 has to be at least as big as 0. Means X has to be at least as big as 1. If I sent a 1 to F, would I be okay? Yes, because I'd have a 0 under the radical. If I sent that 0 result to G, would I be okay? Yeah, because I have 2 times 0 plus 5. This you got to slow down and think about. So I'm saying the domain for the whole thing would be what? And you got to go back and say, okay, if I send a 1 to F, I get the square root of 1 minus 1, which is the square root of 0, which is 0. That's a perfectly good output. Is that output, does it work with G as an input? Yeah, 2 times 0 plus 5 is just 5. Anything bigger than 1 work? Yeah. Notice that the things I have in the black circles, those are our composite functions. They're not the same. The order matters. Let's look at another one. Let's turn up the weirdness dial just a little bit. Okay, two functions. It looks like both of them are going to have restrictions. So let's start off with f of g of x. So I'm looking at again, I like writing it like this better because it shows you what you got to do first. All right, so every place in f that I see in x, I'm replacing with g of x. So I've got 5. Here's what's coming in from g. Plus 4. I've got little fractions all over the place here, so let's try and clean that up a little bit. So now on the bottom down there, I need to get all of that over one denominator. What looks like my common denominator would be x. So that means I've got to multiply this by x and this by x, which gives me 1 plus 4x over x is my lower denominator. Good so far? Check my algebra. And then we do what? We keep. I'm keeping the 5, changing to multiply, and flip. I think that's my composite function. Double check me. Okay, now let's go back and say, what restrictions are we looking at on these domains? So the domain of f. Any values x cannot be in f? Yeah, thank you. So f has a restriction on it, -4. How about g? X can't be 0. Okay, so we've got those two restrictions looking us in the face just right off. So now I'm looking at our composite function here, 5x, 1 plus 4x. And I've got to say, two ways of looking at this. What value could G send that would break this? One way of looking at this is, all right, I'm getting a value from G. So this 1 over x, what would be the bad value I'm getting from G to break F? -4, right? So one way I could look at it is to say, well, from G's standpoint, I don't want that to happen, right? From G's standpoint, I don't want the G function here, the 1 over x, to equal -4 as an output, because then I'd be sending the -4 to F. I don't want that thing in the blue circle to give me an output of -4. So I'm writing it like this, 1 over x equals -4. I want to find the value of x going into g that would do that. Here's one way of looking at it. So I've got what? 1 equals -4x. Or, another way to say it is x is equal to -1/4. That's one way of looking at it. In fact, that's the best way to look at it. So let's just leave it at that. Okay, x equals -1/4. If I sent a -1/4 to g, what would I get? I would have 1 divided by -1/4. I keep, change, flip. That means my output from g, if I sent g a -1/4, I'm going to get a -4 back. If I send that -4 up to the red circle, F, I'm going to get a 0 denominator, which breaks the whole system. All right, so what's my domain for the whole thing? It's kind of tricky. Writing it the long way, in interval notation, I could send g negative infinity, right, or all the way out to that. Up to what? -1/4. Union -1/4 to 0, because I can't send g 0 either because of this up here. Yikes. Union 0 to infinity. Now that's the long way to write it. That's interval notation. Holy moly. The short way would be what?
X cannot equal -1/4 to 0.
So let me get rid of this for a second. Yeah, the short way to write it is x not equal to -4. No, for this one, x not equal to -1/4 or 0. That's a short way of writing it. So all the zillions of values that x could be, it just can't be -1/4 or 0 going into g. Let's turn it around. And then we'll pause and see if anybody's got questions about these two. So my composite function is written in the black circle. The domain written out in interval notation is one way to write it. In just a lot more compact form, tell me the things x can't be. So down here, I'm saying I want g of f of x. So that means our input is going to f first, and then the output from that's going to g. Okay. So what does that mean? That means every place in g where there's an x, I'm replacing it with f. All right, so I've got 1 over 5 over x plus 4. Let me do it a better way. Here's what's coming in from f. So what's in red there is coming in from f. I'm going to keep change, flip, and I get that. So I'm multiplying these two things. So I've got x plus 4 over 5. I'll write it in black. Stay consistent here. There's our composite. Just looking at that, are there any restrictions at all going on? Could x be literally any value? Okay, so now, once I know that x in the black circle could be any value, then I've got to backtrack and say, okay, I'm sending a value to f first here. Are there any things I just can't send into f? Yeah, there's just one. I can't send f a negative 4 because that would break f, and then I'd have no output going to g. So my domain for the whole thing here, short way, is, no, I don't want to do that. Short way is negative infinity to negative 4, union negative 4, infinity, or short way, I could just say x not equal to negative 4. So as you might guess, so we're sending something to G, we're getting an output, we're sending that to F. So that means that equals, every place I see an X here, I'm going to replace it with the output from G of X. So I've got 2X minus 2. Well, that just turns out to be it, doesn't it? So there's our composite function. Not too bad. Let's look at the domains of f and g. The domain of f by itself. Any restrictions? Yeah, it's got to be, the x there has to be at least as big as 2 and could go to infinity. Because I'm subtracting 2 from it. If just f by itself, if I send it a 2, I've got the square root of 0, which is fine. Anything bigger than 2 works also. For g, any restrictions at all? No. But now for this little guy, 2x minus 2, take the square root of that. Any restrictions? So you have to say, what x going into g is the cutoff point there? If it were 0, I'd have a negative 2 under there. Let's see. So I could say, well, 2x minus 2 has to be at least as big as 0. One. So let's check. If I send a 1 into G, up here in the blue circle, if I sent a 1 into that, what do I get as an output? 2. If I send a 2 to F, over here in the red circle, what do I get? Square root of 0. That's fine. So 2 works. I'm sorry, 1 works. Would anything bigger than 1 work? Let's try 3. Just for example. So I'd say 2 times 3 is 6. I send that to F. 6 minus 2 is 4. I get square root of 4. I get 2 as an answer. Yeah, that works. So the domain for the whole thing would be what? X has to be at least as big as 1. Not bad. Let's flip it. We've got just about enough time to do that. So now I'm saying G of F of X I'm looking at G. Every place I see an X, I'm replacing it with the output from F. So I've got 2 times. Here's what's coming from F. And that's pretty much it. There's my composite function. And I could say, all right, since F is coming first, what numbers do I have here that I could send to F that wouldn't break it? So anything 2 or bigger? So I'm just saying right off the bat, let's say, would 2 work? If I sent 2 to F in the red circle up there, what would I get as an output? 0, because it'd be 2 take away 2, take the square root, 0. If I sent 0 to G in the blue circle, I'd get 2 times 0, 0. That works. If I sent anything bigger than 2, that would work. Last thing, before you put everything up, just take note of this. Don't ever assume that f of g of x is going to be the same as g of f of x. Most always, they won't be equal. They weren't on any of our examples. If you go back and look at the things in the black circles all the way back, they weren't the same. So don't make the false assumption that they're going to work out the same. The order matters.